Okay. We all good? Refreshed? Excellent. So a bit of a mixed bag in the first session. Next session, 2 speakers before lunch. Be good. One of the other sponsors came to me during morning tea and said, hey, but we've got a thing going on too. So I'm telling you about their thing. So you can win some automation light bulbs from the folks at Go Wireless. So just rock up to their booth. There's a wee little iPad. Put your details in there. They won't spam you much. And then you'll go in the draw. That draw will be made tomorrow after lunch, so it'll be in the first session after lunch. And same rules will apply. If you're not here, you don't get it. Cool. So first speaker in this next session is Francesco. Great. Clicker thing.
Right, so good morning, everyone. I'm Francesco. I'm from Italy, so you'll get 1 hour of perfect Italian English now. And yeah, so I'm presenting, I have the pleasure, I'm really excited to present the Blue project. It's a project that is running in Eolo, an Italian ISP, since a few years now. It deals with the definition and the implementation of a software-defined network for the Eolo network. So let me briefly acknowledge the work of my colleague. We are actually 5 people who are working in this project in Eolo. I'm also pretty sure, by the way, Alberto, the guy over there, is also in the audience. I'm pretty sure very few of you know something about Eolo. Well, indeed, if you start from New Zealand, you need to go back to Europe, as I said, and then there we are, almost the other side of the globe. And yeah, you need to zoom on Europe, and then we're roughly there, between Milano and Varese. So Eolo is a fixed wireless access ISP. And in the beginning, roughly 10 years ago, it was born with the mission of bringing broadband connection for rural areas in Italy. At that time, outside the big cities, it was really hard to get a decent connection, right? And so that is why Eolo was born, to bring that decent connection outside big cities. And then it was born in Varese, so very northern part of Italy, and from that point, spread it out. And today we're covering more than 90% of northern Italy, and we're covering more than half of central Italy, and we're expanding the coverage of our network. The number of customers, I'm pretty sure, is a bit underestimating what we have right now, and we're doing pretty good. So we have 13,000 new customers per month, and we had this pace running for quite a long time, and we hope even to increase these numbers. So just for those who are not really familiar with the fixed wireless access world, if any, but oversimplifying the structure of the infrastructure we have, we bring connection by establishing links across the country using these towers. And these towers have some radio devices at the top that are used to establish point-to-point links, high-capacity microwave links that are used to connect the towers together, called base transceiver stations. And then there are also devices establishing point-to-multipoint links, and those are the connection of the customers that are connecting to the Eolo network. To the ground, you have router switches, power devices, and so on. And now, if you want to draw a graph of our network and you place a blue dot where we have a BTS and then link together these blue dots, you get really the shape of the northern part of Italian country. So it means that you need to have like coverage and bring this technology in the country. You need to have a capillary network that is spread out over the country. Now, we ended up with this fancy graph by following an opportunistic approach, which means that whenever we found out a new site where it was convenient to have a new BTS, then the price of establishing all the links that were possible, like linking the new site with all the other sites that were in line, and it was possible to have a link, a decent link, then the price of having this link was just about having the price of a couple of radios. So it's much lower than actually having a wire cabling the connection. And so in the end, we ended up with the network with a wireless backhaul mainly, and except very long edges like this one that goes down to Rome, or the ones that goes in the furthest point of the graph, which are fiber links that are used to reduce latency. All the other links you see in this map are wireless links. So this network has some specific features, and we need to find the Blue project address this kind of feature and creates the SDN infrastructure to face the challenges we have for this network. So the first challenge is the diameter of the network. So if you plot the BTSs in terms of their distance from the core, and distance I mean the best path, so the shortest path you have from the BTS to the core, you see that you have a diameter of 28 ops, and the point up there is 16 ops away from the core, and we're speaking about 16 wireless hop, not fiber links, except perhaps the link closest to the core could be fiber links, and then everything goes wireless. The second one is that we have a very dense, highly meshed network. If we draw an histogram where we plot the number of BTSs based on distance from the core, you see that we have much of the BTSs are between 0 and 5, of course, but it still goes up to 16, as I shown before. And if you combine this graph with the average mesh factor, it means the average number of neighbors each BTS has, then you discover that even in the tail of this histogram, you still get an average mesh factor of 2.5. It means that at that distance, one tower can see 3 or 4 other BTSs, and you need to handle this. It's not straightforward. Another challenge, if we want to draw a graph where we plot the number of LLDP events we may register in our network, it means the number of times one BTS in our network see a new neighbor or see the neighbor disappearing. We get this graph, and in a window of 2 days, I think these are the worst 2 days in the EOLO history, we have at most 16 minutes without a topology change in the entire network. And the reason we give to this phenomenon is that radio links kind of suffer bad weather conditions, and so since we're covering like 500 square kilometers of Italy, and then it may happen that somewhere in Italy there is a thunderstorm or something like that, and then that link fluctuates, for example. This is half of the story, so you may see new neighbors or neighbor disappearing. The other half of the story is that you cannot rely on the bandwidth of these radio links. So the bandwidth can change for the same reason as before. And in this case, for example, I'm displaying the bandwidth of one backhaul link we have, and you see at some point it goes down from 800 megabit per second to 400 megabit per second, and then it comes up again. Another pattern you can get is this one, where it stays down, and then at some point it grows up. So you have more bandwidth there. It can also be asymmetric, meaning that on the transmission side, you have fixed bandwidth, downlink bandwidth fluctuates, or it can even be more messy, like in this case. So imagine to have traffic going on this link. You really have to be aware of what is happening and try to reroute that traffic to a more stable link. Now, since we have this highly meshed network, we have many paths connecting the links together. And now the main question here is, how can you efficiently exploit this high mesh factor in the network? So yeah, the title of the slide says the scary news. What's the scary news here? Is that our network, we have more than 2,000 BTSs, grew up as a huge layer 2 pervillance spanning tree domain. Right. Yeah. I'm not joking. And why is it so? Because it grew up so fastly, we didn't have the time to think about what was the best solution for this network. And it's like you having something that burns in your hand and you want to cool it down, but you don't know how to cool it down, actually. What are the consequences of having this huge broadcast permanent spanning tree plus domain? The number of MAC addresses is huge. Is there a way to handle PPP, DSCP, and provide connection to the customers? And how to balance the traffic? So which solution can you adopt? And this is not an easy question. I mean, if you apply like a link state routing protocol, I mean, OSPF, can you imagine one area with 2,000 routers in one OSPF area? It won't scale, right? If you use BGP, it simply will saturate the best path. So you need something in between, and yeah, what do we have in between? So at that time, well, we had to think about what to do about these issues, and at some point, yeah, we realized we had to go back to the hardware level and think about what we can do, followed and inspired by other projects, where they went back to the hardware level, they reimagined the hardware, and think about, can we find a new way, a more efficient way to exploit hardware that we have or we can buy to solve our issues. So, and this is the time where the Blue project started. And the Blue project has three main components. The first one is the hardware. So we had new routers built for us by a US company. Then we thought about the operating system that we wanted to run on this hardware, and then a controller we wanted to build to control our network. And so the next of the talk, we go through all these 3 points and see how we applied and which are the solutions we implemented to address the challenges we have. So back in 2013, we agreed with a US company called Tylera to have these routers built in a few thousand units. And what do we have? We have a 72-core CPU on it, a decent amount of RAM and disk. They do not require a huge amount of power. So recall that we are installing these towers in very remote areas where you don't have much power. So 90 watts in average was a good trade-off for us. And they have 24 1-gig port and 2 10-gig ports. So when we got this router at home, we immediately tested them. And what it means, so we took this router to a lab, and then we tested against electromagnetic fields, just to see, since they're there working under these radios, we wanted to see whether they were working in the correct way. Also, we tried to bake the routers to see whether they were working at the right temperatures, and because these routers go up in the mountains, but also, I mean, close to Milan, we'll have a BTS, and in that case, the temperatures are much higher. And so we tested them for temperatures between -15 Celsius degrees and +75, and we found that they were working correctly. So now that we have the hardware, which kind of software do we want to run on top of them? Then everybody, I think, agrees with me. Nobody wants to reinvent the wheel or do everything from scratch. So we looked around, and we found this company, French company, Six Wind. They are the guys behind the PDK framework. And they sell this Six-Wing-8 operating system, which is basically Linux. We wanted to have some open source stuff on top of that, like Open vSwitch, PPP daemon, DHCP relays, some routing daemons from the Quagga distribution. And then they also have this framework, DPDK-based framework, that allow you to select which cores of your CPU are responsible for handling traffic, the incoming traffic on the ports of the routers. And this is quite convenient for us because every BTS has a different task to do. Like if you imagine a BTS which is very close to the core, it receives traffic from one 10 gig port, for example, and then that traffic has to be spread out on the other ports. If you go further away, like to a BTS with a lot of access, then it is like the other way around. It receives backhaul traffic coming in from the other ports and needs to deliver the traffic to the clients. And so we can configure differently the routers based on the point in the network where they are deployed. And then we also wanted to get the source code of this operating system. Why? Because we wanted to have tons of customizations that were really tailored to our needs. And so we had to improve the way Open vSwitch learns the MAC addresses, and yeah, I have slides about this later. We also implemented some RFC supports for the QAG BGP daemon. We have some smartness on these machines, meaning that they are able to check their configuration. And they're very remote, so we don't want to send people there trying to understand what is going on. So the Blue itself, the Blue router itself, is able to check the configuration, understand whether the configuration is good enough to make it working, at least be reachable from the headquarters. If not, you have a set of steps along which the Blue router checks different configurations. At some points, eventually, it is reachable again from the headquarters, and so we can check what is going on remotely and restore a working configuration. We also have tons of monitoring daemons, like, again, the LLDP daemon, understanding who are the neighbors. We can measure the bandwidth of the radios by querying the radios. We get the bandwidth they can offer. We also measure the amount of traffic that is going on all the interface of the router. So this is the operating system that, with immense creativity, we called Blue OS. And next step is the Blue gateway or the SDN controller. And so why we wanted to build the SDN controller? First, it was to avoid, or at least limit as much as we could, the human error. So we don't want people, or our colleagues or ourselves, to log in the SSH on the machines, play with the configuration, see what is going on. We don't want to do that. We want to have a system that has implemented the task we need to run on our Blue routers, and then this system performs all the tasks that need to be performed on the Blue routers. And so it has all the features you may want to have in this kind of systems, like you can execute in parallel several commands, you can schedule some commands to be executed at night, so if you have very intensive tasks, or if you want to reboot some host, apply some upgrades or patches. It has a way to check whether some changes, or the changes you want to apply, succeeded, and so you can commit the changes, or something went wrong, so you need to roll back to a previous configuration. It has also a way, so it collects all the data that are sent from the Blue routers to the SDN controller. So he knows the topology of our network. He had tons of statistics, logs, error messages. He can raise alarms, and of course also visualize statistics. So there are a few screenshots. Now, in this one, for example, this is a queue of commands that have been scheduled. Some of them have been already executed, and you can see the kind of command, the time of insertion, the time of execution, whether the command succeeded or not, and then by clicking on the command, you can check the logs and other things. We have OES running on the Blue routers, so you can edit the template, the flows you have installed on the Blue routers directly on this system, and then somebody else can review these flows and check whether they're fine or not, and then deploy the flows massively on the network. It has a CLI to query the system itself. So in case of statistics, we can get all the interfaces of our Blue router, and for each interface, getting the configuration, the revision of our configuration, the amount of traffic for each interface. You can check the load on the cores of the CPU, for example, based on the ports. So here you see the ports, and this sums up the load for all the cores dedicated to that port. You can also check the temperature of the board, so understand whether the situation is correct or not. So now we use these three tools combined together to address the issues I talked before. And so the first one, as I said, wireless link as a backhaul and huge layer 2 domain. So by using these blue routers, at least we are able to limit the very high number of MAC addresses. It means that if the blue router has the PEP server DHCP relay, then you prevent many MAC addresses to be forwarded to the core. The blue itself stops these MAC addresses, and then by BGP, then the blue can advertise the IP pools he is managing. If you use multiple backhaul VLAN, you can kind of balance the traffic. So if you have an overloaded link and you are using different spanning trees, you can have different ways for reaching the destination point from the core. And this is what we call the phase one. So the solutions we were able to apply with these blue routers at first. There are still some issues, as you can imagine. So we are not able to change the cost of the ports for different VLANs automatically. We have to do it manually. So our colleagues sit down, look at the network, see where the route of the blue is, and then try to change the cost of the VLAN on the ports to have different spanning trees. Second, we still have quite a lot of MAC addresses for each blue, so more than 1,000 MAC addresses for each blue, and this is kind of bad for the blue routers. So we were able to fix the second point, and the issue comes up because if you have these three blue routers that want to speak together, and this one on the left who wants to speak to this one on the right, then the one in the middle will create two flows, and the two flows are matching precisely the input port, source MAC address, destination MAC address, destination port. And it's not hard to see that if you have many blue routers speaking across the one in the middle, this number explodes. It grows quadratically in the number of the blue routers you have around. And the main thing to notice here is that you don't really want to match the input port and the source MAC address. The only thing you care about is where the destination is, not where the source is. And so by patching OVS, we were able to decrease the number of flows quite a lot. And this becomes, again, kind of linear in terms of the number of blues. It may seem an easy patch. It is not, because in our case, we have these two components working together, like OVS is defining the flows, but then it's not handling the traffic directly. He is kind of instructing the PDK framework on how to handle the traffic. So OVS sees only the traffic that is not matching any flow it created before. And now, if you have this flow here, there's no way for OVS to understand that there are many more blue speaking and matching that flow. It means that if somebody else replies back, OVS doesn't know the source MAC address and the port on which this MAC address is speaking. And so we have to move the MAC learning on the BDK framework and then do a bunch of patches. What's the result of having this patch? Well, we reduced drastically the number of flows OVS is creating per second. If before we had around 800 flows per second created by OVS, after this patch, this number goes down below 100. And this has a series of consequences for us. First of all, if you have many flows, the router is really unstable. So it means many packets are dropped, and the router struggles in creating these new flows continuously. If you have very low number of flows, these flows get matched much more, and so the router is more stable, is not overloaded, and we get a better result, a better overall result. So yeah, this one is the phase one, and we were able to survive until now with this phase. And next, what's next? We thought about a second phase, like how to get rid of this huge layer 2 and move on, have a smarter solution for our network. And so what do we know about our network? Well, the SDN controller knows the link capacity, the residual bandwidth for all the backhaul links, and then it knows also the desired bandwidth. It means the amount of traffic Blue with an access radio has to deliver to the customers. So the first idea you can get is that, okay, you can get a centralized controller deciding the flow, like the routes of the traffic, and then program the Blues with the correct flows for handling this kind of traffic, right? He knows everything, so he can decide what to do. And the solution builds on OpenFlow rules for MPLS label switching, and then you can use this RFC with BGP for labeling the traffic. This RFC allow you to advertise a prefix in BGP with an MPLS label. Okay, so just to make things very simple but clear, imagine you have this simple topology with some fiber links and some radio links on this side. This is the capacity of the link, and if we want to deliver 400 megabit per second on this router, well, the SDN controller can decide, let's do this route, and then instruct first the core to label the traffic correctly, and then write the flows on the Blue routers on the way to the destination. What happens if this link, for example, goes down, so it's not able to carry the amount of traffic we need to carry? Well, then you need to compute another route and remove this flow and instruct the routers to treat the traffic correctly with new flows, right? And so there is an issue here. The issue is that the granularity of the OpenFlow flows is too small for us, which means that if you have one new route, you need to reprogram every router on that path towards the destination. And every time the network changes, you need to compute new routes for the destination and upgrade the Blue. And this is quite a tough task, also because upgrades needs to be atomic, which means that you cannot leave the network in a consistent state. And as you saw before, our network is not so stable for the backhaul wireless links, so the risk of leaving the network in an inconsistent state is quite high. Last but not least, we don't have a big red button to be pressed in case of troubles. So what happens if we discover that our optimizer for the traffic has a bug? What do? There's no way to revert to a standard routing protocol or something safe that may not be optimized, but still it runs, and it runs safely. So we had to stop a minute. We tried the solution, and we saw all these issues, and think about what is the bad point in this case. The bad thing in this case is that the network is completely passive with respect to the controller, so it has to be thought about everything it has to do. Okay, so the third phase, which is the one I'm speaking about the next slide, simply wants to add some smartness to the network or make it less passive with respect to the controller. And, well, it builds up on the segment routing paradigm. And then, okay, we added an IGP running on the routers in the end. And we selected eBGP with this RFC that allows you to advertise a prefix with an MPLS label. We still have this RFC on the core for labeling downlink traffic. And then the point we are building is that we are still using MPLS label switching, but the BGP daemon on the blue router itself is instructing, is creating the flows on the blue router for handling this kind of traffic. So no one has to instruct the blue routers on what they have to do with that traffic. And so if you go back to the topology we had before, at some point where BGP converges, every router knows what's the best path, the shortest path for reaching the destination. And in this case, you don't even have to optimize the traffic, right? It simply follows the shortest path, if that's fine with you. If not, so how to optimize our traffic? Well, our SDN controller knows the topology of our network, the bandwidth, how much bandwidth we have, and how much bandwidth we need to deliver to the customers. We just need a new point, a new piece of information, which is the routing tables of the protocol that is running on the blue routers. So now, taking all this information, feeding it into an optimizer, you can find an alternative way for delivering the traffic to the final router. And now, notice you don't have to source route. Segment routing is source routing, but you don't have to source route the traffic hop by hop, but you just need to find like 1 or 2 waypoints and then exploit shortest path between these waypoints. And this means that, for example, along the flows for reaching R7, we learn also the flows for reaching R6. And then if that link goes down, then the optimizer may say, let's go first to R6 and then up to R7. And the way it has to do that, you just can instruct the core for the correct stack of MPLS label, right? And then the traffic will go first down to R6, along the shortest path, and then up to R7. And there are good points about this solution. First, we don't need to program from scratch the blue and instruct them with the correct OVS flows for handling the MPLS label. They automatically learn the flows for handling the MPLS labels. And the optimizer comes into play only in case of congestion or in case one path is no longer available and the other ones are not sufficiently big to carry all the traffic they should carry. You have, in this point, for building the optimizer, you have tons of tools you can use and you mixed up. So I'm just mentioning a few of them. And then you can apply a lot of heuristics. It means the experience we have in our colleague who changed the cost of the several VLANs for getting new spanning tree. This knowledge can be kind of implemented in the optimizer, and so will be something really tailored for our network. Last but not least, we do have now a big red button we can push in case of troubles, like turning off the optimizer reverts to the standard shortest path for BGP. And this may not be the best solution you can get. Again, it will saturate immediately some path, but at least it will work, and we'll have a way to debug what is going on and adding, for example, one flow after the other one, and then restore the way the network should work. So we are running experiments about this third solution. They're very promising, so we hope to be in production as soon as possible. And along this new idea for routing the traffic, we have some more points in the agenda in the Blue project. The first one is the new hardware. Like on many important sites we have in the network, we ended up piling many Blue routers because we needed more than 2 10-gig ports of one single router. And this is no more energy efficient. Instead, one, say, Super Blue will be both power efficient and offer the network capacity we need on those important sites. We are searching among x86 architectures, and then we will port all the work that has been done on the Blue routers on these new machines. Second, we are moving on and switching from Quagga to FRR, which is a fork Quag. I'm pretty sure you know about it, and now it's well maintained. So we hope even to contribute to this project and push the changes we implemented. We can also devise like an optimization, a more fine-grained optimization, such that we're not treating all the traffic equally, but trying to understand which traffic may benefit from a path where the latency is lower, and move the traffic that is not delay aware, like internet, web browsing, to another path that is longer, and this will again optimize even more the way our network runs. Another point we get almost for free is the communication blue to blue. If now we spoke about only downlink traffic, then if we want two blue to communicate among each other, then the only thing you have to do is label the traffic from the source blue with the correct label of the destination, then the traffic will go right away. And you can have also a stack of labels, so the optimizer can optimize also the blue to blue traffic. So yeah, this is pretty much what the Blue project is about. And I think I'm ahead of time, so maybe we have time for questions. Of course, if you are interested in the Blue project, do not hesitate to write us, and we would love to hear feedback or discuss with everybody has something to suggest, or yeah, get discussions. That would be extremely wonderful for us. So thank you very much.
Yes, knew the beast.
Thing to say that some people actually did hear about that. The Ivan Pepelnak, I think, made a podcast with you guys. I don't know who was there at the time, but I'm not sure.
Which one?
Ivan Pepelnak, I think. At some point, there was a podcast about that, saying about
yeah. Okay, I got it. Yeah.
All right. And the second question, like, what about the IGP part? How are you actually getting the traffic statistics? Are you using the traffic engineering extensions for an IGP you're using for SPF or IS, I believe, or you are just discovering by just pulling statistics off the interfaces somehow?
So you mean how do we get the routing tables from the router?
The bandwidth information, right?
The bandwidth information, we can query the radios, SNMP, and then the radio replies the bandwidth.
But for links themselves, so all your routers have the the links between themselves, right? And you have the information. Traditionally, on MPLS network environment, that information is carried in IGP, in ISAS or SPF.
Yeah.
Right, but that requires extensions, which I think by default in Quagga there's no such a thing. It doesn't exist. So, and how do you actually collect that information? Do you just like collect from the routers like SNMP or something from the router itself?
Yep.
You just do that.
Yeah.
Okay. And then you feed it into controller, and controller then
exactly
does that.
Yeah.
Okay. Right.
The capacity of a microwave link can change from second to second. How much time do you take before you decide whether the change, how often are you polling the radios to find out what their capacity is, and how often are you adjusting the topology based on the capacity changes?
Well, you need to have like thresholds, otherwise you keep computing new solutions, right? So you have thresholds, and then when the threshold is you go over, so the bandwidth is not enough anymore, you need to compute another solution. And right, so the question is how fast do we compute another solution? So right now is a matter of seconds, even less.
How long does it take that topology change to propagate through the network?
Well, I mean, the topology change, you mean the new flows on the routers. We didn't so much traffic getting lost in our experiments. So it works.
may have turned it. Oop, I didn't turn it off. I may have missed this, but do you publish the BlueOS code anywhere, like on GitHub?
No, actually, we can't do that because so the BlueOS code is done mainly by these French guys, and they have their own license.
So you've licensed the code from Wingate?
Yeah. We have the 6 Wingate code. We are working on it, but we cannot publish it on GitHub, for example.
Okay.
I think all New Zealanders know about Les Blues. I think we all know how they play the game. Cool. So more? That was a rugby joke. Sorry, wrong crowd.
Hi, Hendrik from Marnet. Can you just tell how many people and what sort of period of time have been involved in this evolution?
How many people are working in the Blue project, you mean?
Yeah.
5. Like those displayed at the beginning. And we're 5 people. Then there are other colleagues who are helping us, like if we need to discuss something on the experiments, we have some results, and we can go there and say, hey, as I said, all the expertise we had from the networking people who are actually handling the traffic and this VLANs, we speak with them quite a lot and get expertise out from them.
Thanks.
More? Nope. Thank you very much.
No, thank you.
Cool. And so next up we have John from Crown Fibre Holdings, all right?
Yeah, Crown Infrastructure Partners.
Oh, Crown Infrastructure Partners, my mistake. Talking to us about, I assume, RBI2 and UFB2 or something like that?
Yeah, UFB and RBI.
Excellent. Give them a big welcome.
I have to be careful what I say here now because I've got all the wisps here, so I can't say the wrong things. Also, Claire was here this morning, so I have to be careful about saying the wrong thing and contradict that too. So what I'm going to talk about is RBI and UFB, how it's going. So you'll see some numbers up there. At times you'll say the numbers don't add up, and that's true, they don't always add up. And that's because it's hard to actually get accurate data sets for what we're doing. So as long as you don't try and add up all the numbers, they are mostly right, but they don't always add up properly. So just for a quick snapshot of the project, with UFB 1 and UFB 2, that means 87% of New Zealanders will be able to get fibre by 2022. 86% of that's built by UFB 1 and UFB 2, but there's about 1% of the country's covered by other people building fibre. I mean, Chorus is building Gore, we're not funding that. And Spynet's got fibre out there. Electricity Ashburton's building fibre, so there are quite a few people building up there. Our uptake's approaching 40%. That was in September, it's actually past 40% now, nationally. We're doing over 15,000 connections a month. If you take a working day, that's over 1 connection a minute during a sort of 8 a.m., 6 p.m. That's quite a lot, and it's growing. You know, in December, doing about 1,000 connections a day. So the project's running reasonably well. People say, why is it only 40% and not more? The project hasn't finished yet. There's not a great awareness. It's a case of building up the resource to actually do the connections is one of the things, and also every connection is a construction project. You've got to go out there and build something. So RBI2. RBI2 covers a lot more land. It's wireless based. We're not building fibre. No one's offered yet to build fibre for the RBI projects. There's some fibre going to the backhaul, but not into the access networks. So covering about 70,000 households and businesses. There's 900 kilometres of state highway that are programmed to be covered. State highway black spots and over 100 tourism locations. And we're completing that project by 2022 as well. Just another view of the project and timeline. So UFB 1 is covering POP about 3.7 mil. This is where the numbers at the bottom, if you take this is a 2023 population projection, and that number at the bottom don't quite add up, and that's because they're roundings more than anything. And also, because we take premise and convert that to population, which isn't an exact science, but it is, the numbers are roughly right. So it came about 3.7 million of the population UFB1, and then we add the UFB25, which is 530. There's a whole bunch of network out there already, and there's VDSL, there's wireless, there's all sorts of other technologies which deliver broadband already, and that's another 520,000 people get that outside the fibred areas. And then RBI2 is aimed at covering the remainder, which is 151,000, which is covered, plus and then there's another 33,000 gap, which is left at the end, which is about 0.7%. That means at the end of RBI2, there'll be 0.7% of the country left without broadband. And that seems like a really good number unless you're part of the 0.7%, right? Then it's not so good at all. The part of this is, as Claire mentioned earlier, when you've got 0.7% gap, you've got to think about what's the best way to spend your money to close the gap. Because if you've got an internet penetration of 80% of households, which is a number people often use, I don't know if that's the right number, it seems to be about right, 80% internet penetration around New Zealand, then the gap of people who don't have internet who can have it is much bigger than the gap of people who can't have it and don't have it. So if you look at the UFB2, the UFB uptake, so this is UFB1 and UFB2. This is the September quarter, it's grown since then, so in December it's higher. I just didn't get the December numbers into here. And UFB is actually building about 50 towns. I say about because it's hard to actually decide what a town is. If you take Auckland, it covers Pukekohe and it's got Waiheke in there, and there's Waiuku separate. Sometimes people call that part of Auckland or not. So you get into what's a suburb and what's a town. So in here we've got 34 towns. The average uptake here is now in December is above 40%. The blue lines represent those areas which aren't complete. And you'll notice there's blue lines scattered in both above average and below average areas. And people try and look for correlations about why is the uptake higher in some areas than others. And there isn't really a correlation. It's quite easy to explain Capita, because Capita's got a very, very high penetration of the Voda HFC network. They already get quite high broadband, they get their cable networks, so there's not and Capita also isn't complete, so there's not a huge demand in Capita for fibre. But if you take the socio-economic things, Whangarei is a low-income area, but that's doing really, really well. That's up in the top 3. So there's no correlation between completeness, no correlation between household income, so it's very hard to understand why take-up in some areas is higher than other areas. It's just is. And so now I get on to UFB and how we look at New Zealand. So this is a population density graph. It was first developed by a guy called Andrew Douglas Clifford. I saw it in a newspaper and I thought that looks pretty cool. I can use that. What it does is essentially take New Zealand, turn it into 1 kilometre square blocks, and if someone lives in one of those blocks, it gets coloured white. If no one lives, it colours green. So this gives you a good view of New Zealand where no one lives in New Zealand, and there's lots of New Zealand where no one lives. So what we're trying to do is fill in with our funding as many of these white blocks as we can and turn them into provide broadband in those areas. And we started that with UFB 1, of course. So UFB 1, and this also is UFB 1 and 2, covers about 50 towns for UFB 1, 3.7 mil pop, that's 75% of the population. Then UFB 2 came along, that's about 340 towns, about 530,000 pop. UFB delivers a gigabit per second to the homes. It's fibre based, everything in there is fibred. People say people don't use a gigabit a second and can't use it, but the uptake of gigabit a second is around 7 or 8%. We start out with 30 megabits a second. When we first did this, people say we don't want 100 meg, we need 30 meg plans to introduce people, and we picked 30 meg because it's more than VDSL did then. Of course, VDSL 2 does more than that now, but we started with 30 meg plans, we say we don't need 100 meg. Well, now 30 meg was about 80%, 90% of the uptake. Now it's 4%, so 4% of the penetration. 100 meg makes about 80%, then there's 500 meg and 1 gig. And so the majority of fibre is on 100 megabits a second. We roll this out per premise. We don't look at population for the rollout, because we pay per premise. When people roll out, we pay them for a premise, not for covering population. And when we're trying to just figure out where all the premises are, it was actually really hard, because there's no one set of data in New Zealand which covers all the premises. So you end up looking to say, where do people live in New Zealand? Where are the premises? So you start with the LINZ land data, and you get a database saying, here's all the land parcels. But some of these land parcels are really big, right? And you can't actually tell where the premises are those land parcels. And this is another area of data uncertainty, because you don't know how many premises on a land parcel. Let's just take the Auckland Airport, the UFB 1, it's passed, and it's one premise. And that's a huge area, and so you know there's more than one premise in Auckland Airport, right? But it is called one premise for our purposes. So that's produced some interesting sort of numbers, and also when you get into the rural areas, it creates other problems, because when you've got a farm and you want to go and plonk, you don't know where to plonk the pin about where the premise is, and you start designing radio sites, you don't know if it's in line of sight or not. So you say that land parcel has got coverage to it, but it's the land parcel has, we don't actually know the premise has. So again, when we start saying what you've covered, we're pretty sure the land parcel is covered. We can't always guarantee the premise is covered, even though we then went through some rating information, we went through some additional information to look where building outlines are. So it captures a lot of it, but there will be fringes where the data, again, the data is not quite right, but overall it's pretty much on track. When we're doing this and look at the population sort of things, when we're doing UFB 1, the distance between premises, so to pass a premise with fibre, it was about 18 metres roughly across the initiative per premise. When you get to UFB 2, it's more than 25 metres. It just gets more and more expensive as you go along. And then if you again further fibres get ridiculously expensive. I think in UFB 1, the biggest, or the longest area was Fielding, which I think was about 22, 23 metres per premise. And so that's why people aren't looking at building fibre in some of these areas. If you look again at UFB 2, you're getting some really small towns here. You're talking about Punakaiki, which has got about less than 50 homes in it. You're getting places like Lake Hood, 168 people live in Lake Hood. So when you talk 87.5% of the country, you're talking some very, very small towns. It just gets unfeasible to build fibre into places that are smaller than that. So people say, we want fibre in our town. Well, you've got 5 people live in your place, so you're unlikely to get fibre. Part of the problem is getting backhaul there, because you've got a fibre access network. It doesn't make sense to have a long, thin radio network, a backhaul network feeding it, even though those are getting pretty good now. So UFB 2, the last, just covers some larger towns, Motueka, Stratford, they've got now 7,000, 5,000 people in there, but the majority of these UFB 2 towns are actually quite small. So then we knew the areas were built with fibre. We had a very, very good view about every premise that was fibred. So then we look at where some of the people live. These are people who get broadband. We actually took broadband in our RFP. We released the RFP was 25 megabits a second. There's a lot of uncertainty in when you're asking about how much speed do people get, especially on wireless networks, so and also DSL networks. So we're looking for anyone who gets greater than 20 megabits a second. That's why this says greater than 20, even though the RFP said greater than 25. And trying to figure out which premises don't have broadband is actually quite hard. We could easily figure out which ones, some of the ones which did, which are all the ones who are fibering. But the ones who don't was actually a tricky proposition. So we actually went out to all the network operators we could find, and there was lots of them. I mean, there were just lots and lots of this, is where we met lots of the WISPs. And we asked, where do you provide broadband? And that, of course, is not as easy as you think it would be easy, but some people say, well, here's all the address points we provide data to. Other people say, here's all the power meters we have that we provide address points to. Some builders have 2 power meters, some don't have any. And another company said, well, here's all the copper pairs we have in our network and where they are. And so you may have 1 or none connections there, so that doesn't necessarily help either. And then there's all sorts of other ways of how people actually count their premises, and it's very hard to actually assign locations to them. So it was quite a large GIS exercise involving lots of shape files about where these people actually are in New Zealand. And then we took all these shapefiles and compiled this. As you can see, this now fills in a whole bunch more of our white dots. So when you do this, you're getting into it covers about 520,000 people, another 10.5% of the population. So getting up to 95, 96, 97% of the population is now covered with broadband, if you're talking about broadband of 20 megabits per second. And it's a case of, so we probably have the most complete data set of where people are, with those fudge factors around some of these. We can't identify exactly where on a land parcel the users are. So we look at RBI2 expansion and fill in some of the other white dots. We released the tender in 2016. We started signing people up in 2017. There's still another couple of people who want to sign up. They're not included in these numbers. So there's still a gap. Some of that gap will be filled. But you get into smaller and smaller numbers as you go along. The remaining gap after this is still 16,500 end user, about 33,000 people. There's a difference between the end user and a person, because the end user is the premise. We deliver the service, the end user is the people inside it, or the population is the people inside who use it. This is all wireless. A lot of this is the WISPs delivering this. The rest is the Rural Consortium Group, the RCG, made up of Vodafone, Spark and 2 Degrees. I said before, none of this is fibre. There's some fibre going into backhaul networks, but not long runs of fibre. It's mostly short runs to meet existing fibre networks. And it's a mixture of 4G LTE, which is the MNOs, and fixed wireless, and some of the WISPs are starting to use LTE type technology. And we've got, for the rest of the gap, because there is still a gap, so if you look at where's the new gap, it's harder to see them, but there's still lots of white dots. You get more and more dispersed. You end up with a population density dropping down to about from 850-ish per square metre in UFB, down to about 9 people for the rest of the gap. So this is about 4 or 5 premises per square kilometre is what you're trying to address. And the problem, one of the problems is getting people to want to build in these areas, because it comes away from a CapEx problem where we can fund a site. So you can give them money and build a site, but then they've got to get enough revenue off that site to actually pay their ongoing costs to run the site. If there's a fault, I mean, you have to get some on there. It just blows you can blow years worth of revenue. You've got batteries to look after, you've just got general wear and tear maintenance to actually carry out. So getting bids is hard, and trying to find ways to fund it is hard too. So we've asked all the people who respond to the initial tender, who had bids in, to ask them how we can go about closing this gap. And we're expecting responses due in the sort of first quarter of this year, and we'll see how that goes. Some of the things about getting into wireless, there's land acquisition. You can't always get the land you want, so if you you make assumptions during the whole planning process about where the land's going to be. If you have to move that, suddenly you've lost some of your population. You need to get access to that site. Some of these are quite remote, so there has to be road there or helicopter access. If you're building a big tower, there's a lot of concrete delivered by helicopters. That's not particularly easy either. Power. If you're building small sites with a single operator, then solar can work. If the RCG and you're building a site that has to support 3G, and you still need 3G for mobility services because a lot of handsets don't support 4G, and you've got 3 operators sitting on there on 3G, it's a big tower, and you're taking lots of power as well, so you're not going to be running that off solar, so getting power up there is expensive. Getting backhaul there is also hard. This is all radio backhauls. We're actually building quite a few towers which are just repeater towers for backhaul. And then, of course, there's support and maintenance, ongoing support for those sites. So it's quite a challenge. The more remote you get, the more challenging it gets. Luckily, we're not building it. We're just asking other people to build it. So I get all the hard work. I wasn't sure whether to show this slide or not because it looks sort of like a corpse, someone who's died of measles or something and then got infected with maggots. But the lines are actually the state highways where we're building networks. The grey lines are the ones we've allocated in the contract, and the red lines are unallocated roads, state highway roading. And this is about 1,040 kilometres of roads that have been done. There's another 1,000 or so of roads still to do. So there's still a lot. Getting into black spots is actually harder than doing end users because the business case is harder. If you look at the ratio of black spot sites to RBI sites, it's about 5 to 1. So you need about 5 RBI sites, the revenue off that, in order to fund the black spot sites. So it's funding black spot sites gets a bit harder. That's just the ongoing operating cost, because with, of course, the 4G LTE stuff, you've got to pay the licences as well as the batteries and ongoing town and land lease costs and stuff. So when we were doing this, we were only targeting state highways, so we weren't doing all the local roads. We were looking at things like accidents. By the way, we didn't do the prioritisation. The prioritisation was done by the ministers. We're an implementation group, so we take the policy stuff and we implement that. But some of the ways is done through public safety primarily, so looking at public safety for roadways and visitor numbers. And some of the areas we haven't done, which will be part of the next bid set of things, like in the Napier-Taupo Road, where it still snows and people get stuck in the snow. So we really want to build that for public safety purposes. Franz Joseph's one of the priority areas, and the Alpine Passes. And in the black spots, some of those were public safety, the end of track ends for search and rescue, and the rest were mostly visitor numbers. That's how we do all the black spot stuff. And in the tourism black spots, we've covered 108. The black spots are allocated in the contract. I say allocated rather than contracted, because in the again, you have to get the land in order for it to actually build it, but they are allocated and we're quite confident they can actually get built. So here's some gratuitous pictures. So this shows some of the sites that have gone up. The first two from Wiz and Rangatamu, Flat Point. So Flat Point's covering about 5 or 6. Is the Wiz person here? Wiz? No, so it's Flat Point's covering about 5 or 6 people. It's in the Wairarapa. Gisborne built quite a large tower that took 6 or 7 truckloads of concrete into there, and then built quite a large tower. Since got new pictures showing with all the antennas and aerials and stuff hanging off it. This is Moonshine Valley. Moonshine Valley wasn't built by us. This was funded by Vodafone. It was something they did in Moonshine. So you can see that yellow dot's where the site is. And there's about 28, 29 premises in that valley, and it's a wooden pole with solar power. There's more panels on there. Could just be because the 3Gs and the 4G radios take more power than the smaller WISP equipment, and you might think something like this is quite easy. I mean, they had the land there, but getting the consent to build was the problem. It took ages to get the consents, because you have someone objecting, saying the solar panels might reflect sunlight through my windows, so I don't want that. Please take it somewhere else or take it away. And then when you've built all these things, you can see there are trees in the place. So again, once you've built all these, you've put in the right, got the land, you've got the towers up, and you point to a house, there might be a tree in the way which might block it. So it's not an exact thing when you're doing all this location stuff. And I mentioned the RCG. And the RCGs, again, Vodafone, Spark, and 2 Degrees. They've formed a consortium to roll out RBI and black spots. And in RBI 1, they were doing some backhaul sharing and some site sharing. They don't always share backhaul, but I think it's pretty common. And so there they've got a lot of duplication. Duplicate the core network, radio controller, and the node Bs and Spectrum. So in the Mocha network, the multi-operator core network, they share a lot more stuff. So they don't share their own cores, and they're offering individual services, different service levels, different pricing, different plans. And what this enables a lot more efficiency. So it reduces the power requirements, it reduces the duplication, therefore cost. And spectrum sharing is one of the big things too. Because you can share all the spectrum together, if you can get 30, 40, 50, 75 megahertz of spectrum in here rather than the individual spectrum allocations. Now, it's not free to use the spectrum because, of course, you still need all the antennas and radio systems and stuff, but by sharing the spectrum, it gives a lot more spectrum into these areas, and they are a lot less densely populated than some of the areas in urban New Zealand. So again, delivering broadband services should be a lot easier here than delivering in urban areas. It's got more spectrum per person. So that wraps up presentations. Are there any questions?
Hi, Mark Frater from Compass Communications. Is there an opportunity for WISPs to deploy like picocells that connect to the RCG network?
That's something you have to take up with the RCG. It's not something that's part of our project. The RCG, in our agreement with the RCG, they are building a network which allows co-location and backhaul sharing. We haven't talked about connecting to their core networks.
Anyone else? Oh, yes. You good?
It's a little unrelated to your deployment schedules, but we need to talk about burst sizes.
About?
Burst sizes.
Talk away.
Particularly around using UFB or RBI fibre as backhaul to local WISP deployments. What you tend to get on some of the particularly cheaper ones is that packets in the network tend to bunch up, which means that we get replies that are very bursty, and the bursts exceed the burst sizes, and you don't get the throughput you expect to get.
Yes, I agree.
I'm putting it out there. We need to talk about it.
Is anyone from the Whispers who'd like to comment? Because when we've seen what we've seen is that I'm on RBI myself. I live in Waikanae, but I'm not covered by fibre, never will be. And my service varies from about 50 megasecond to 70 megabits a second. I haven't noticed any throughput problems.
I've worked on some where you can sell. If you run throughput tests from the radios to the radios, they get what you expect, and the moment it crosses the UFB path, or the RBI path rather, fibre path, the throughput just completely drops out. A lot of that has to do with the gear being used, but we end up with very bursty performance. Burst sizes are too small.
We're running ahead of time. This goes wrong. So, nothing more questions. Yep.
Just curious, are there any other Americans in the room? Or am I it? Okay, we've got one other one. This is more just a comment, because I'm busily Googling all this stuff. I live in a pretty rural section of North Carolina in the United States, and I am lucky to get 10 megabits. And I know this because I have screamed at my provider, and I've got like backdoor connections, and we can keep it going. There's absolutely no initiative in our government to serve rural parts of the country. And so I just think it's amazing to be in a country, and I mean, I just came here from Australia, and they're doing similar things with the NBN. I mean, it's just like, oh, I put my foot in that one. I put my foot in that one. But anyway, I did not mean to do that. But it's just really cool to see this kind of initiative in the world, because as the MP said this morning, lack of internet access is a new sign of poverty. in the world. And so it's just cool. I mean, I know you guys have problems to overcome and there's issues with bursting and things like that, but anyway, it's cool.
Yeah, we've been very lucky here that we haven't had a really partisan approach to this, so we don't have all the political infighting and change in direction all the time.
Does Italy have any government support for rural broadband?
Yes. It goes region by region, and there are the government has some actions, and there are applications to get fund to cover the region with some technology, and then every operator brings the technology. And we were able to win, I think, 4 regions and
5 from the last year.
Yeah. So you want to?
No, yeah. We won the 5th region last year, and we participated to this founding, but we with wireless technology, some with fiber technology, VDSL. So is more operators that brings different technology. So it's not only wireless for the rural areas.
Isn't legislated? Are you doing it because the government tells you to, or are you doing it because you think you can make money?
What?
So do you have to by law? Are you required to by law? Or is each regional?
No. I mean, you apply to get fund for that region, and then if you win, the government gives you money for building the infrastructure, and you need to prove that you covered high percentage of all the buildings around. So you're bringing. We're lucky because we have fixed wire access. We can get very close to the rural areas, and as I said, so Italy has this chain of mountains in between and all these kind of things. And so we're kind of have an advantage with respect to those who have to dig and take the fiber there.
Okay, so John Brewer, the biggest problem that I see with using fixed wireless, and I'm a wireless guy, it's my life, biggest problem I see is traffic caps. And of course, Chorus is publishing these statistics all the time saying that, well, the average New Zealand household is using 750 gigabytes a month now, or however much they are using. And they're breaking it down by city, saying, well, if you live here, you're using 300 gigs. If you live here, you're using 120. I don't think the traffic caps on existing RBI plans are anywhere near that. What are the traffic caps going to be like on the new RBI 2? And if you're investing $150 million in a system that can't deliver the same traffic caps that everybody else is getting, how are you going to tell the people, well, you can have internet, but you can't really use it?
Yeah, I know the problem with my traffic cap is 120 gigabytes. So how much traffic do people use here? How many people use over 500 gig? Lots, yeah. A month. Yeah, no, it is a problem. What we're seeing is that, what we're thinking is that there's 3 operators going to be able to compete in each of these regions. And also there's a lot more spectrum available to them, just because they're doing the mock-in system. So therefore it enables them, we think, to provide higher traffic caps if they want. I think the bigger problem will be that if they provide higher traffic caps there, they'll have to provide higher traffic caps across the board, which could become harder for them.
You said that the take-up rate varies between 30% of premises and 50 by town, with an average of around 40, 45, 48, right?
Yep.
What's the percentage of folk who, no matter what, even if it was free, even if you sort of knocked on the front door with the fibre, would not take it? In other words, there's sort of the folk who are being serviced, the folk who have alternatives, and there's a pool of folk who just would not ever. And the reason why I ask is a study by AT&T, who are doing a rollout in America because of this whole deal with Yahoo, found the figure in America, it was 25% of premises would not take a broadband fibre service no matter what.
We don't know. This is one of things that Minister Curran was alluding to earlier, that she doesn't have a really good data set of that. She doesn't know what the economic gap and the don't want it gap is.
But isn't the cost of rolling out a service really dependent on the take-up rate, the number of prems you pass and actually take up the service? Because the folk who do take it up have to pay for the complete rollout. Those who don't take it up, you know, are basically adding to the cost of the ones who do.
Yeah, I think the internet take-up rate in New Zealand's around 80% of the figures I've heard. I don't know how accurate that is. Does anyone have a better number than 80%? But that's been around that number for a long time. So when rolling out the networks, the people who are rolling it out take that risk about the take-up rate. Like when the business case was originally done, it was done a lot less than 40%. Okay. And if we know what the cost per premise passed is on the fibre network, and we therefore know what the average revenue per unit has to be to take that, to cover that cost.
Okay, thanks.
You're a good speaker, Jeff.
I was going to say, Jeff, there's a lot of older people over 75 or 80 now that live at home that don't want the internet. They get it on their mobile phone if they really want it, but a lot of them just don't want it at all. So they don't sign up for a UFB or even a DSL service. Some of them don't even have a phone line now.
With the lion's share of the money going to Spark, Vodafone and 2 Degrees, is there any intention to provide regulation for wholesale access and pricing like you do with Chorus, or the intention to look at wholesale pricing in the future to make sure that it's competitive and that there is some form of open access to smaller providers?
So there is open access for smaller providers onto the towers for co-location service. And there's also agreements in the contracts around access to backhaul services, and the Commerce Commission's undertaking a study on backhaul services now. We're not looking at setting anything in the contracts around access to the core network, but there are requirements on telehouse or co-location on the towers.
Yeah, because it's a decent amount of cash you're giving away there.
That's right, and we're funding those towers.
Cool, thank you.
We'll try it. Awesome. Thank you. I'm Mike from GNS. I live in Wellington, in the city center of Wellington, in a big apartment building. I'd love to be connected to fiber, but Buddycorp has declined many times. And I went around the building, I asked our neighbors, there's more than 50% which would be willing to be connected to fiber, but Buddycorp just doesn't allow it. Do you have any way how to convince the property managers and Buddycorp companies to, roll it out?
No, it's an ongoing problem about property rights, and there's the Land Access Bill, which was put in earlier last year, which gives some additional rights for accessing property without getting the consents and things like right-of-ways and high-rise buildings, but it's very hard to actually use. Like, it's all very well to say you've got the right to go and connect apartments 23B and no one else wants it, but really, unless you've got some way to kick down the door and get in, it's just not going to work, right?
Thank you.
So it's there to help, and it's available to be used, but it's still going to be an ongoing issue.
Back on the question about open access to the towers, is there a limited charging regime that they're allowed to do with those towers? Like,
yeah,
do they
the
own
way
that
the
tower?
contract was set up is that we're funding the capital cost of the towers, and the RCG can charge the incremental cost of maintenance on the tower, and if there's a land access charge, they can charge a portion of the land access charge, but they can't charge a capital contribution towards the tower itself. Well, it's what we fund, so basically when we fund stuff, it's covered.
Is CFA to look at what reasonable costs are for interacting with the mobile companies? For example, I had a quote this week for $2,700 to install a single PowerPoint at an RBI 1 tower.
No.
You're not going to look at that.
No, look, in the contract itself, there's particular things set around, some things are set about what they can charge, and it relates to what we fund. When stuff we don't fund, we don't try and regulate those.
So is that inside the Comcom's remit for their work?
I'm not sure exactly what Comcom's remit is, but it's the place to start, I'd imagine.
I can see John writing a letter as I talk. Anyone else?
Richard Nelson, you mentioned the way the speed of access has evolved on the fibre network from 30 up to 100, and it's going towards 500 and gig. The radio networks that you're currently defining it as somewhere between 20 and 25. Is there any view as to how that might evolve over time?
Oh, there's always things like 5G coming along. There's better radio access, but it's always a cost to deploy these things, and also you're limited by signal-to-noise ratios, by spectrum. So it gets harder and harder to do it on wireless. And so you can increase the modulation rates, for example, but that just makes them less stable, and therefore they can't go as far. So you have to build more towers now, so just keep on building more and more towers. With the population density so low, you end up struggling to build the towers, and then as you get up to a gig, you have to start building fibre backhaul to them. And once you've got fibre backhaul to a tower which is serving one person, you might as well just carry on, right?
Cool. Oh, one more.
Darren from Lightwire. So the current, like for RBI2, you want the local WISP to be able to deliver, say, 20, 25 megabit. Do you see, say, in 5 years, revisiting RBI and saying we want to invest in, or help you invest in infrastructure to deliver 100 meg to rural properties?
The wrong person to answer that.
Right.
We've got a set of policy objectives we try and implement, and if those policy objectives change, we'll try and implement those new policy objectives the best we can. So, but we're not setting the policy objectives, so a future government might decide they want a higher bandwidth. But I think competitive pressure will tend to improve the data caps. They will tend to just improve the general speed and access as well.
Cool. And after you, I think we'd have a bunch more questions for her. Interesting. You're good?
Okay.
Excellent.
Cool. Thank you very much.
So some good conversation starting. That's good. Everyone's starting to wake up, get going. It's good. So we're going to have an hour of lunch, and we'll see you back here at 1:30. 1:30.